Hi everyone, welcome back to the channel. If you don't know me, my name is Ryan, and the purpose of my channel is to help you pass the FE Mechanical exam. Today I'd like to go through the solution to this problem with you guys. We're going to use the official FE reference manual and just solve this problem step by step. The first link in the description below will take you to my software FE Interactive, where you can solve this problem for free, as well as all the other problems that I solved in my FE exam playlist. I highly recommend you go ahead and solve those problems and get a refresher of some of the important concepts on the FE exam. I hope you went and tried all those problems. Let's get into the solution here. It says a crankshaft accelerates uniformly at 3/4 of a radian per second squared. During this motion, its average angular speed is 1750 RPM and its final angular speed is 1930 RPM. How long does it take to reach this speed? Okay, so over here, I have down some references, and one thing I want to talk about in this video is the three important relations that you need to know that'll make all kinematic problems simplified. You won't have to really check in the reference manual, so it'll be super quick if you know these three relations. Before we get into that, let's go ahead and write down some of our givens. You can always break down the problems into something that you're given and something that you need to find. So I recommend you go ahead and try to do that. It says a crankshaft accelerates uniformly, right? So what that means is that we have a constant angular speed. We're talking all about rotations here, so that's why we're looking at angular accelerations, angular speeds. So it makes sense that I would write the alpha here. It says accelerates uniformly, so we know that's a constant value. And we know that's a constant value of 3/4 of a radian per second squared. During this motion, its average angular speed, that's the angular speed omega, is equal to, and that's the average, 1750 RPM, rotations per minute. Its final angular speed, the final speed that it reaches, is equal to 1930 RPM. How long does it take to reach this speed? We're looking for the change in time between the initial and final speed that it takes to reach that kind of final speed. We know the average speed, the final speed, and we know the angular acceleration rate. Now I'm going to show you guys a different kind of technique. Of course, we can go into the reference manual and find all of these equations for a constant acceleration rotating body. But you could save a minute or two here if you just remember some of these relations here. Now these are for particle rectilinear motion, but they're analogous to the equations for rotational motion, and they work for constant accelerations as well as non-constant accelerations. Any kind of scenario that you have, these are the general equations. If I think of what I kind of have and what I need, if I write down the rotational analog to these, all I'm doing here is replacing A with alpha, V with omega, and S with theta. Now, if I look at what am I given? I'm given a angular acceleration, omegas, and I'm looking for time. The kinematic relation I need to use here would be this one. So if I go ahead and write that down, what I have is the time rate of change of the angular speed is equal to alpha. If I go ahead and move that dt to the other side and integrate, I have the change in the angular speed. The difference between my current angular speed and my initial angular speed is equal to a constant alpha times my change in time. Okay, so I have this first relation. This one I'm going to call equation 1. If I check off what I know and what I don't know, I know the alpha value. I know the final omega. I don't know the initial omega, and I don't know the time. What other information were we given that we're not utilizing yet? It's this right here, that the average angular speed, the sum between the initial angular speed and the final angular speed divided by 2, the average speed, that's equal to 1750 RPM. Now, I usually don't go ahead and plug in values at this point. it just helps me save time if I just do everything in equation form. So this is my second equation. I recommend you do the same thing. Okay, so all we need to do here is we need to go ahead and find some kind of relation for omega naught. If we go ahead and solve for omega naught in that second relation, or the initial angular speed, it's just double omega average minus the final angular speed. We can plug this into the first relation and solve for that delta t. So we have omega minus omega naught. If we plug this in, 2 times omega average minus the final angular speed is equal to alpha delta t. What we're looking for in this problem is the time difference between the final and initial time of the motion. So what we have is, if we simplify this a little bit, this becomes a plus. We have 2 times omega minus omega average here, doing that algebra and dividing by that alpha term. So this is going to be our final thing that we plug into. You can see that we have everything. We have the final speed, we have the average angular speed, as well as the angular acceleration. Now the whole thing comes down to some units. Now if we go ahead and plug into that delta t relation, we have 2 times omega was 1930 RPM. Omega average is 1750 RPM. I go ahead and keep track of some of my units here. I have rotations per minute in the numerator. What about the denominator, that alpha term? I was given it as 0.75, and that's radians per second squared. I recommend you go ahead and keep track of your units separately so it doesn't get confused inside of all the numbers. This is a way I use to keep track of all my units, and it's been really helpful to me. I recommend you do the same if you're struggling with some unit conversions. If you're enjoying the video thus far, please consider leaving a like and subscribing for more content like this. Let's go ahead and finish up this question. Let's go ahead and check that answer here. 50.26 seconds is pretty close to 50.3 seconds. Check, and we can view the explanation and quickly kind of review what we just spoke about. So the first thing that we realized was that we had a constant acceleration process, and using those 3 kinematic relations, we can really get to anything that we need to get to. We saw that we had omega information, we had some alpha information, and we were looking for time. So we used that first kinematic relation to get this constant acceleration equation. We thought about the definition of the average, and we're able to solve for that initial speed. Knowing the initial speed, we plugged it into our first relation, and we were able to find that the uh, time necessary after some unit conversions is 50.3 seconds, corresponding to choice A. We go ahead and check in the manual just to show you it's kind of there as well. Under the constant acceleration on page 104, just like the reference says, just like that reference says right here, what we see is that alpha relationship that we basically use here. Omega minus omega naught, the final minus the initial angular speed, is equal to alpha delta t, and we essentially use that equation along with the definition of average. If this problem was helpful for you, please leave a like and subscribe. Thanks for watching. I'll see you in the next video. Goodbye.